So we are still currently in Unit 1 Kinematics. We are still currently in Part B, Motion with Changing Speed. We haven't talked about what speed is. We do have usually an inherent understanding of it based on our driving experiences. But I think it's important that we now start looking at these things a little bit more specifically. For example, when things appear to be at rest or moving, can be determined based on what is called their frame of reference. How fast an object is moving or not moving is going to be based on the frame of reference that we use. A car approaching you as you are driving as well is going to seem as if it's going faster than it actually is. That's because both vehicles are approaching each other. If you are going, say, 55 miles an hour, and a car approaching you is also going at 55 miles per hour, it would be the equivalent, or need the time, as if one car was stationary and the other one was going at 110. Because when both things are happening, that requires that amount of time. Now, many of us have probably been in a car and watched the scenery change out the window. Think back to a time in which you have been in a vehicle recently or back when you would look at the road outside your car door. And it looks like the road is moving very fast. It's moving away from you, but the road isn't actually moving. What's moving in that scenario? The car, right? The car's moving. The road doesn't move. So, for that frame of reference, but it looks like it's moving fast. You look out into a field, and things don't seem to be moving as fast anymore. The farther away you look from your car, the slower the objects seem to be moving. And that's all based on frame of reference. None of them are moving, they just seem to be moving. Tree isn't moving too much unless it's in the wind, or there's a pretty good tornado going through. Okay? So when we look at this picture here, we can say we're seeing a train moving from left to right, and you're standing on the side watching it go by. Somebody that's walking from left to right as the train goes from left to right, are they going to look like they're going fast? Or they look like they're going to go slow? Or are they going to look like they're going the same speed as if the train was stopped? They're going to look like they're going fast. It might not seem, though, that they're really going very far. It will look like they're really going fast as if they're going opposite. They're walking against the motion of the train. Because now all of a sudden, they're like, oh, okay. You can think of this as if you're walking down a down part of the escalator. Right? You're moving, but you're trying to actually have to move faster to get ahead of the escalator a little bit. What seems like a never-ending, well, rat race would be going down on an up escalator. But in a train like this, because it's moving, the person is going to seem as if they're zoom, going faster. Okay, so it's all about the frame of reference. When we're dealing with things in this class, Earth, we can always know is moving. That's a scientific fact. And it's always rotating. But because we're on the Earth, we don't see like it's moving. But it is. Just like when you're in the car, the ground looks like it's moving, not the car. But it's the car that's actually doing the moving. So we have to be careful of that. We can put this in perspective. If you're in an airplane, or even in a car, and you flip a coin, if it's going at a constant speed, what does the coin do? Just acts as if you're at rest. Now all of a sudden, what happens if you speed up? Where would the coin go? Would the coin go this way or that way? The coin, if we all of a sudden sped up, would probably hit the person in the picture in the head. Okay? The coin doesn't want to move. It's going to want to stay in the same path. If all of a sudden something changes, it's going to come back at them. Or if it broke, it would move the other way. Such is the case if you have stuff in the back of your pickup or in the back of your car and you slam on the brakes, where does it all go? Whoosh, right? Why? Because it doesn't want to change. Okay? Remember, one of those old dead guys that we talked about how motion doesn't want to change. Something has to force it to change. Objects that are moving want to stay moving. Remember we talked about inertia, Galileo. Okay? What we want to do is we want to describe the motion more thoroughly. A word we can use for that is speed. Speed is how far an object travels in a given time interval. Okay. If you see an equation in a box, that is an equation that should be on your equation sheet. Your equation sheet is going to help you find these needed things faster, instead of trying to flip through your notes forever trying to find something you didn't or you forgot to write down. Speed is one of those. Speed is a scalar quantity. No, I spelled that. Speed is scalar, meaning just gives us magnitude. No direction. Any combination of the units. In physics, we tend to use meters per second much more than any other. You can also use kilometers per hour. or miles per hour. And some of these we will try to at least get you to think about meters per second, but then also tell you what it would be in, say, miles per hour, just to give you that realistic approach of what does that mean in these terms. Average speed is the distance that you traveled over a given amount of time. So a car doesn't always move at the same speed. This is pretty given. Some of you know it probably more than others. You can tell that the speed, for the most part, your speedometer is pretty close to instantaneous speed. But does have a slight lag as well with it, but not much. So it is pretty close to as instantaneous speed as we can get in a real world situation. So the speed at a given instant is instantaneous speed, meaning we want time, the time interval or the change in time, we want it to be very, very small. Okay? Because that is going to give you a more picture of what the object is doing at a very given specific moment in time. So let's try some of this out. Let's solve the problems, so to speak. When we do these, we want to make sure that we're showing as much work as we can. Why? Well, it allows me to give you partial credit. Meaning if you just write an answer, I don't know what your brain's telling me or how you came about that. That's why writing it out, showing me what it is there. So a car travels at 60 kilometers in 30 minutes. What is the speed of the car? Okay. Now this one seems very straightforward in that we are told, say our distance, travels, distance, 60 kilometers. We're given a time of 30 minutes. How many of you would convert that in your head? One person in class, so nobody in the Zoom. So what we have here is some will want to convert that into 30 minutes and keep it as such. Some will go half hour or just 0.5 hours. Are we going to get the same answer? Yes and no. Yes and no. We're asked to solve for the speed. Well, Well, the equation that we use told us S is equal to distance divided by time. Now, that's the formal one that we can use. There are others. You can do what's called a circle equation. I've also seen them as triangles. What do we do with these? We cover up what we're trying to find, and it tells us the equation in what we have. So, if I'm covering up my S, the only things that I can know now are D and T, and it's D over T. If I'm solving for T, it says what is the time? It tells me that it's distance divided by speed. If I'm looking for distance, it's speed times time. It takes a lot of the algebraic manipulation out of the issue. And sometimes that helps out, not having to think about it. So it does not matter which one of these that you use. You have three options for the equation. It does not matter which one you use to me, as long as you're using one. Well, we're going to solve for speed. We're going to use the distance divided by time. I substitute my knowns in. And I get 2 kilometers per minute. If I did it the other way, and used hours, things are going to change. But what mainly changes is my labels. The actual speed might look like, you're like, most of us would look at this and say, oh my gosh, that 120 is going so much faster. Is it though? Is it? No, it's going the same. Going the same. So we have to be very careful on when we look at these about what is the label. Okay? Because about 55 miles an hour is about 20 meters per second. And you're like, well, the bigger number doesn't always mean that it's faster. Okay. So, person runs 100 meters in about 11.2 seconds. What is the speed of this person? 11.2 seconds is probably close. It's a little bit shy of qualifying for state in Minnesota in the 100-meter dash. But sometimes should be able to get you into the finals, maybe top 2 in the section. But it probably won't win it. Usually you got to go close, a little bit lower. You never know. Some years are always different. But it's the same thing. Distance, it's 100 meters. Time, in this case, seconds. Speed, well, that's what we're looking for. The equation that we're going to use again, does not matter which one. Oops. That you use, the same. And that speed is equal to distance divided by time. 100 meters divided by 11.2 seconds is going to give me a value of 8.92. I would say 8.93 meters per second. I'll keep my colors the same there. If a cheetah can maintain a constant speed of about 25 meters per second, it will cover 25 meters every second. How far will it travel in 10 seconds? Or how about 1 minute? Well, that requires us to think things through a little bit differently. We have a speed of 25 meters per second. How far will it go in how far? How far is always a... How far is a distance question. The time is going to be 10 seconds and then 1 minute. And 1 minute means how many seconds? 60 seconds. We need to be able to convert that. The equation for speed, again, is speed is equal to distance divided by time. Or we use the circle equation, cover up, and we can see now that it is speed times time to give me my distance. So 25 meters per second To get that distance, we multiply to get 250 meters. That's moving. To get 60 seconds, we do the same thing. We just have to change the time to give us 1,500 meters. Now, cheetahs usually don't run that far. They will only hold it for maybe 10 seconds. Short bursts. They're not going to be running a mile at that 25 meters per second.